Welcome, differential equation students. This is the second lecture in our series, and it's going to be on graphing differential equations and slope fields. So now that we have an idea of what a differential equation is, now we want to understand what it means to graph a differential equation. Okay, so the graph of the solution to a differential equation is called the solution curve. And so what we want to do is we want to understand how it is that we're going to utilize the differential equation in order to, in fact, draw the solution curve. So the first thing that we're going to use is we're going to use something called a slope field. So a slope field is a graphical representation of the DE. So each differential equation, we generally are going to start out with like dy dx equals something, okay? And we notice that this here, that's the differential equation. That's the derivative. The derivative is the slope. So what we're doing in a slope field is we're going to draw the slopes at particular x's and y's. And what's going to seem a little bit different here is that not only are our slopes oftentimes going to change dependent upon x, they're also going to be changing dependent upon y. Okay, and I'm going to point that out because that actually is going to make a big difference in terms of understanding what's happening to the differential equation as we increase in terms of x or as we increase in terms of y. Which one is dy dx dependent upon? Okay, so let's take a look at an example. So let's say dy dx equals 2x squared. Now in this case, this is only dependent upon x. So as x gets bigger, dy dx gets bigger. So the slopes are going to get larger as x gets bigger. Okay, so that's what's going to happen here. But as y gets bigger, nothing happens to x. Or excuse me, nothing happens to dy dx. Okay, and we should say this gets bigger. So as x gets bigger, dy dx gets bigger, but as y gets bigger, nothing happens to dy dx. So we're going to say that that's dependent upon x. Okay, and we can see, like, say for example, we'll take an x and a y. Right, so we'll have some x, we'll have some y, and then we'll have dy dx as our slopes. Okay, so when x, for example, is -1 and y is 0, we get dy dx is just simply equal to 2. If x is -1 and y is equal to 3, on the other hand, dy dx is still equal to 2. Okay, because we just plug in, right? This is going to equal 2 times -1 squared. And again, it'll be just 2 times -1 squared. But if I change x now, say for example I let x equal 0 and y equal 2, then I get 0, because that's 2 times 0 squared. Okay, 0 and 5, I get 0, because again, we're just 2 times 0 squared. We're just having that dy dx is just dependent upon x. Okay, and it's going to be really important, because as we change x, what's going to happen to the slope? On the slope field, we're going to end up getting these same slopes. Okay, and then let's say for example I have 1, then I have 3, say for example, then this is going to be dy dx is equal to 2, because it's going to be 2 times 1 squared. Okay, if I have x equal to 2 and y equal to 155, what I'm going to get is dy dx equal to 8, because dy dx is going to equal 2 times 2 squared, okay, which equals 8. So if I imagine what I'm going to look at here, okay, is I'll draw a graph, and what my slope field is my slope field is going to be a drawing of each one of these values for dy dx. Not the values for y, not the values for x, but the values for dy dx depending upon the y and the x. So I go in here, and when x equals 0, I end up with, right? I end up with dy dx equals 0. So I'm going to draw just straight lines. And you can see I can draw these straight lines all the way up, right? Even in between my hash marks, which I'll do. Okay. And so we have slopes equal to 0, whether or not it's negative or positive. So when x equals 0, dy dx equals 0. All right. Now when x equals 1, or actually let's start with -1, what we get is we get a slope equal to 2. Okay. So if I redraw that, what I'm going to get is I'm going to get something that looks basically like this. Okay, that's a slope of 2, a slope of 2, slope of 2, 2, 2, 2. And notice we're going upwards. Same thing when I have y negative. Right, the slopes are going to end up being exactly the same. Y is going to equal to, dy dx is equal to 2. Okay, so we could actually write that dy dx equals 2. Over when x equals 1. When x equals 1, we can see that we're going to have the same slopes. So I basically should draw them exactly the same. Okay. We can draw them all the way up and down the line, right, as dense as I want them to be. Okay, so I draw in my slopes to give a real clear sense that no matter where I am at on x equals 1, the slope is going to be consistent. The slope is going to end up equaling 2. There it is. And then when we see that, like say for example, x equals 2, then we get a much steeper slope, right? Our slopes kind of look like this at 2. So as long as I'm on that line 2, I'm going to get the same slope up and down the line. Now, since this is x squared, I'm also going to get it at the negative value too. So I make that slope, each one of those slopes is going to be exactly the same, no matter where I draw it on the line x equals 2. And that's it. And that's basically what a slope field looks like. We'll look at some of these inside of Desmos in just a moment. So what I did now is I just plugged into Google. I plugged in slope field generator on Desmos. And we click on the slope field generator. And now, just to give a better sense of what this is going to look like, in the slope field generator, you'll see a function, gxy. That's just another way of writing dy dx. And then what I'm going to do is I'm going to put in my 2x squared. And what we can see, just like I said, is go ahead and take a look here. As I go up along x equals 0, I have constant slopes, a constant slope of 0. As I go up along x equals 1, my slope there is 2. We can even look at it. You can click on it. So there you go. You see 1, 7. Okay. Right. That's just an equation for our slope grid. As we move over, you can see their slopes increasing, increasing, increasing. And in fact, this is going to help us out quite a lot as we start to look at what's happening with our solution curves. Okay, and let's actually talk for a moment about solution curves here on this particular graph. So now we're taking a look at what this is our slope field. And so let's just imagine that we follow a curve. Okay. And so I put these in my notes so it's a little bit more static. It's not going to move the same way. But if I just imagine, let's say, for example, I start here at this point here, okay? And as I go forward or increase in terms of x, right, my slope is going to increase, 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 increase. And on the same token, or by the same token, okay, as I go in the negative direction, I also see that those slopes are increasing. Okay, and so there we go. Okay, so you can kind of see that that's what the solution curve looks like. All right, start at a different point, you get or a different value for initial condition for y, and what you get is you get a curve, right? Okay, that starts at a different place but basically has the same shape, and that's because the differential equation is exactly the same for both of them. And you can see that this is like a cube curve, okay? In fact, if I took dy dx equal to 2x squared, and I take the integral of both sides, okay, then what I'm going to get is I'm going to get y is going to equal 2/3 x cubed plus c. And you can tell that that's a cubic function that we've got right here. And that's exactly what's going on, okay? And that's what those solution curves look like. Let's take another look at another example. And this one will be kind of different because it'll be dy dx equals to y squared. So in this case, dy dx, our slope, is only dependent on y and not on x. So if we kind of drew our table like we did before, we'll have an x, we'll have our y, and then we'll have dy dx. Now, what we know is we're going to say, okay, well, as y changes, let's take, for example, when y is equal to -1, and say x is equal to 0, what we get is that dy dx is going to end up equaling 2, okay? Because it's going to be 2 times -1 squared. Or if x equals 5 and y equals -1, then we get dy dx to equal to 2 again, because again, it's going to be 2 times -1 squared, okay? This kind of seems similar to the one that we just did, and in some ways it is, but in other ways it's not. It's going to look like very different in terms of graphically. Or let's say, for example, we choose that y equals 0, okay? When x is, say, 11, we still get that dy dx is equal to 0 because we get 2 times 0 squared. Or when x is equal to 12 and y is equal to 0, we're going to get 0 again. Doesn't matter what value I choose for x, what I'm always going to get is that dy dx is going to equal whatever it is, okay, as long as we choose the right y. Okay, so let's take, for example, 5. We'll choose 1, and what we get now is we're going to get 2 again, okay? And that's because y equals 1, -1, that's 2 times 1 squared, okay? And so consequently, that'll be that slope right there, okay? So if we look now at our slope field, let's draw it out. We'll do one by hand, okay? When y equals 0, so now y equals 0 is everything on that x-axis. So if I draw out these slopes, let me use a different color here to make sure that it's very clear. So if I draw out these slopes, right, I'm going to see that along y equals 0, I get a 0 slope. Okay? When y equals 1 now, I'm going to get a slope of 2. So say, for example, it looks something like this, and y looks something like this. So everywhere along that line, okay, and we'll actually make them a little bit smaller so you can see, but the slopes are going to be exactly the same, right? And we're basically just drawing some little vectors in there to represent our slopes, okay? Now, what about when I go up a little bit? Well, or actually when I go down to -1, I'm going to get the same slope, okay, as I would at +1. We saw that before. I'd say, for example, now if I went down to y equals -2, I'm going to get a higher slope, a bigger slope, okay? Bigger slope, bigger slope, bigger slope, bigger slope, bigger slope. And notice each and every one of these is positive, so each one of those slopes is going to be positive because it's 2y squared. So you're going to get a positive slope each time, okay? But as I increase y, there's another thing that we can see in terms of behavior. As I increase y, what I get is I get an increase in dy dx. So as y goes to infinity, dy dx is also going to go to infinity. And it's in fact going to go really fast because what we have is we have the y squared term. Okay, so we can kind of imagine that our solution curves are going to kind of follow that particular scale. Okay, let's take a look at this inside of Desmos. So now I'm going to change this in Desmos, and I'm going to change it to y squared. And now what you're going to see is you're going to see something very different. Notice now, down here, along y equals 0, we've got those 0 slopes. And we get an increase in slope as we change y. Not in terms of changing x, but only in terms of changing y. Okay? So what's that going to look like? So let's take a quick snip of this. Now what I can see is I can see very clearly what's happening to this particular graph. You can see those solution curves. We're going to get that as y approaches 0, we're going to actually smooth out because that slope is 0 down there. Okay? And you can kind of see also when we're below y equals 0, you see these graphs, they're going to kind of, you know, very big slope at the bottom. And then as we approach 0, everything kind of like smooths out and evens out. Okay? And so what we get basically here is we get an exponential. We get some kind of exponential. And one of the cool things that you can see about what's going on here is that below y equals 0, we get different behavior than above y equals 0. And that's one of the things that's kind of interesting about these slope fields, and also about when we think about solutions to differential equations, right? Different y-naughts, different initial conditions, give different graphs, at least in terms of their looks. The differential equation is going to be exactly the same, but those solution curves are going to look slightly different, right, depending upon their initial conditions, okay? And that's actually something that's kind of like, is really fascinating about differential equations just in general, right, is that depending upon where we start, we could get a very different looking differential equation. Or excuse me, not differential equation, but very different looking solution curve. Now let's take a look at 3 important characteristics of slope fields that are going to help us in order to find equilibrium solutions and to characterize characterize solution curves and help us to draw solution curves. The first one is called equilibrium solutions. The second are called isoclines, and the third are called changes in concavity. So for equilibrium solutions, an equilibrium solution is any solution to the differential equation of the form y of x equals y naught, where y naught is constant. And what that really means is that this means dy dx is going to equal 0. Where the solution is a constant value. All right? So what we're looking for is a solution curve, y equals some constant, and what we know about that is that if y is a constant, then that means dy dx is going to equal 0. So what we need some value that we can plug into the differential equation that will give us dy dx equals 0, and where y is also a constant value. Okay? So let's take for example, let's take dy dx equals y minus x times y plus 1. If we look here and we set dy dx equal to 0, so we say y minus x times y plus 1 equals 0, then that's going to give me that y is going to have to equal x, or y equals negative 1. Well, in this case, what we have is y equals x is not constant. It's not a constant function, so it's not going to be an equilibrium solution. But y equals negative 1 is an equilibrium solution. So that is going to be my equilibrium solution. And so what that tells me is, along the line y equals 0, or excuse me, y equals negative 1, the slope is 0. And what that's going to be is that's going to be really, really valuable for us, because what that's going to look like is it's going to look like where the slope actually goes to, it's where our line or our solution curve is going to approach but never actually hit. It's going to get really, really close because you can't move off of the equilibrium solution. We actually saw one just a little bit farther up here. Let's take a look at it. Okay, right here, if you remember, along the line, right, y equals 0, we have all the slopes there, dy dx equals 0. And so what you see for each one of those solution curves is that as our graph, like coming up from the bottom, as the value approaches the equilibrium solution, right, we get closer and closer without ever touching. And the same thing goes in the case of going away from it, right? Okay. As we move away really quickly, but as we go towards negative infinity, basically it ends up kind of giving us some kind of like horizontal asymptote. Okay, and that's what an equilibrium solution looks like. When we look at some of the applications for differential equations, these equilibrium solutions are going to be incredibly important. So you want to think to yourself, okay, that's where the slope is going to equal 0, and that's basically going to be where our differential equation is not going to touch. Okay, and that's the equilibrium solution. So the next thing we're going to look at is these isoclines. And what an isocline is, it's the curves on the slope field where the differential equation is going to be equal to a constant. Okay, so let's take a look at an example, right? We had, for example, dy dx equals 2y squared. Okay? And so we'll let k equal a constant. So when I plug that in, I'm going to get 2y squared equals k. All right? So what that's going to tell me is where on the graph, okay, is the slope of the curve equal to a constant value. Let's take a look at what that looks like. Let's say 2y squared equals k. So I'm actually going to go solve for y. So that's going to be 2y squared equals k. And that'll mean that y squared equals k over 2. Okay? And that means that y is going to equal plus or minus the square root of k over 2. So when k equals some value, or excuse me, when we're on the line y equals plus or minus the square root of k over 2, then the slope of the solution curve is equal to k. And so let's take a look at what that actually means. So let's say, for example, we're going to select our slope, our dy dx, okay, and we want to know, right, where does it have that particular slope? So for example, when k equals 0, or dy dx equals 0, we plug in 0 for k, okay, so we get y equals plus or minus the square root of 0 over 2, right, we kind of already knew this, so that's equal to 0. So when y equals 0, the slope's equal to 0. That's our equilibrium solution. What about, okay, if we select another number, let's take k equal to 2. So dy dx equals 2. So this is going to be equal y equal to plus or minus the square root of 2 over 2, which is equal to plus or minus 1. So the slope is going to end up equaling 1, right, whenever dy dx is equal to 2. Or, excuse me, the slope is 2 whenever y equals 1. So slope equals 2 when y equals 1. All right? We could take, again, we could look at, like, say, for example, 4. And so when the slope is equal to 4, so k equals 4, then y equals plus or minus, okay, 4 over 2, which is equal to plus or minus the square root of 2. Okay, and that's basically, this just tells me where it is that the slopes have these constant values. All right, now sometimes it's going to look a little bit different, okay, or it might even look a lot bit different. Like, for example, if we were looking at one of the ones that we had before, let's say we had dy dx equals 2x squared. Okay, now what we get is we'd set this, we get k equal to 2x squared. Okay, and then that means that x squared is equal to k over 2. And then that gives me then that x equals plus or minus the square root of k over 2, right? Which basically means now instead of having horizontal lines, okay, the constant slopes are along the verticals. And we saw that there, along the vertical lines. And so those are isoclines. Basically, we're going to see some examples of this. When we want to solve for isoclines, what we're going to do is we're going to set our differential equation equal to some constant k, right? We might have a value for the constant, or we might not. It might just be a number, right? We'll do that, then we'll go and solve, and that'll tell us something about the behavior of the slope field. The final one we're going to look at is concavity changes. And so concavity changes are just like what you figured out in calculus. They are when the second derivative is going to equal 0. Okay, so basically they're going to tell us when we're going to go from concave up to concave down, and they can really tell us a lot about the shape of the graph. All right, so we want to make sure that we understand how to find those concavity changes as well. And so we'll see some of those instead of our examples. All right, so why don't we take an example? Let's take a look at this one. We'll take dy dx equals y times y minus 2. Okay, y times y minus 2. And the first thing that I want to notice when I'm going to draw my slope field, okay, so I want to draw a slope field, is I want to notice this is dependent on y only. And so what it means to be dependent on y only means that as x changes, okay, we're not going to get any change in the slope field. It's only going to be dependent upon when y changes. Okay, so let's first take a look at our equilibrium solutions. So what we'll do is we'll set dy dx equal to 0. So this is going to be y times y minus 2 equal to 0. And this is going to be when y equals 0 and y equals 2. So the curve will flatten out at both of those places. At both y equals 2 and y equals 0. Notice, right, that these are constant values of y. Not only does the differential equation equal 0, but we have them for only constant values of y. Now let's take a look at isoclines. So for the isoclines, we're going to get y times y minus 2 equal to k, some k value. Now if I look at this, this is going to be then y squared minus 2y equals k, or equals k. And so that's going to then give me y squared minus 2y minus k equals 0. What I want to notice about this is that I can actually use the quadratic in order to figure out what k is going to, or what y is going to equal. So I want to figure out what y is, right, and kind of help me to define what are the values. I already know they're going to be constant along the y's, okay, or the horizontal lines. I kind of want to now know what the relationship between the slope, right, okay, and the values of y. So that's going to give me a equals 1, b equals negative 2, and c equals negative k. So y is going to equal negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times negative k divided by 2 times 1. And that's my quadratic formula. So this is now going to be then 2 plus or minus the square root of 4 plus 4k, all divided by 2. And then I can simplify further. This will be 2 plus or minus the 2 square root 1 plus k, all divided by 2. Okay? And so then this is going to give me then that y is going to equal 1 plus or minus the square root of 1 plus k. Right? For all values of k. Right? So for all values of k, what we are going to have is that k has to be greater than negative 1. Okay? Greater than or equal to negative 1, excuse me. Okay? Or else square root of 1 plus k is undefined. So basically what this is saying is that the slope of the differential equation never goes below negative 1. Right? Otherwise, we end up with an undefined value. Okay? So that's our isoclines. And then finally, we're going to look at our concavity changes. And in order to find our concavity changes, we're going to have to use implicit differentiation. So now we've got y times y minus 2, okay, is our dy dx. And what we're going to do is we're going to take d squared y dx squared is going to equal, and I'm going to utilize the chain rule. So that's going to be dy dx times y minus 2 plus y times dy dx using our implicit differentiation. So what that means then is that d squared y dx, I'm going to plug in the value of dy dx. So this is going to be y times y minus 2 times y minus 2 plus y times y minus 2 times y. Okay? Which essentially is going to equal y times y minus 2 squared plus y squared times y minus 2. Notice that all I did for each one of the dy dx's, I plugged in dy dx. And that's all I really needed to do. Okay? So now, I'm going to do some simplification. I'm going to pull out y times y minus 2. And that's going to leave me with y minus 2 plus y. And so this ends up equaling y times y minus 2 times 2y minus 2. And now that is going to get set equal to 0. So 0 equals y times y minus 2 times 2y minus 2. And so y will equal 0, 2. Y will also equal 2. Okay, and y will equal 1. So these are the changes in concavity. And notice, one of the things that's kind of strange about this is that these aren't points that are changes in concavity, they're entire lines, right? The changes in concavity are going to be at our equilibrium solutions, and then also at y equals 1. Okay, so they're going to be at our equilibrium solutions and y equals 1. That's It's a little strange, okay? But we're going to see what this kind of looks like. Let's take a look at each one of these features, right? We have equilibrium solutions at y equals 0, one at y equals 2, okay? We also have our isoclines, right, are going to be everywhere for all values of y, okay? They'll never be less than -1, and they're going to get bigger and bigger and bigger and bigger as we increase the values of y. So as y gets bigger, we're going to get bigger and bigger values for isoclines. So let's go in, let's take a look at it in Desmos. Okay, so now let's change this. This is going to become y times y minus 2. Okay, and you can kind of see our solution curves. Okay, or hopefully you can start to see the solution curves. You can see the equilibrium solutions. Here's one at 2, here's one at 0. You can also see this thing here, that's y equals 1, that's a change in concavity. Okay, basically we're going to go from concave, it looks like we're going to go from concave down to concave up at that point. All right, because notice that the slope there at 1 is actually negative. Right, that's going to be where our slope is equal to -1. Above 2, okay, we're going to have our slopes increasing at very high rate, right? It's going to look almost exponential. And below y equals 0, what we're going to get is we're going to have them increasing, but asymptotically towards y equals 0. So let's take a look at what this looks like and draw some solution curves in. So what we can see is that we're above y equals 2. What it looks like is they look exponential. Those functions look exponential. On the other hand, when we're below, they also look exponential, but they're looking exponential and they're moving towards y equals 0. So they're increasing towards y equals 0, but never actually hitting. And notice that's the behavior at an equilibrium solution, right? At equilibrium solutions, we get close, but never touch. They're like asymptotes. Like asymptotes, not exactly the same. Then, if we look here, well, notice that we have a decreasing, we have a change in concavity, okay? So what I'm getting there is I'm going to decrease down towards y equals 0. I'm going to start up at y equals 2 and decrease down towards y equals 0. Okay, so it's actually quite kind of different. So depending upon where we have our initial conditions is going to be where the graph looks. It's going to tell us what our graph looks like. So for example, if I start here, right, if I start at y equals 1, okay, then what I'm going to get is I'm going to get a graph that just kind of descends down towards y equals 0. Okay, if I start a little bit more closer up to y equals 2, okay, then I'm going to get one that's going to descend, then change the concavity, go from concave down to concave up, and then again move towards y equals 0. On the other hand, if I start out above y equals 2, what I'm going to get is I'm going to get a curve, right, that's going to go, it's just going to rocket up towards infinity. Okay, so that actually is going to help us to think about how it is, the behavior of these functions, depending upon where you start. Okay, and that'll be really crucial to think about population, or cooling, or velocities, or anything else like that. Okay, so it's kind of neat. Let's take a look at another example. And let's choose dy dx equals y minus x. Now in this case, the derivative is not actually dependent upon just y. It's dependent upon y and x. Okay, so we'll first start out with checking for equilibrium solutions. So we're going to get y minus x equals 0. And so that we're going to get our slopes equal to 0 whenever y equals x. Okay? But y equals x is not a constant function. So this particular differential equation has no equilibrium solutions. So no equilibrium solutions for the d. Okay? What about isoclines? Well, now let's take a look, and we're going to set y minus x equal to k, all right? And let's look at what happens with individual values of k, okay? So we'll take k equal to negative 1, all right? And so that would give me y equals x minus 1, all right? So you just see how that works. Y minus x equals negative 1, and then we just do a little algebra. That's going to be y equals x minus 1 by adding x to both sides. Or say, for example, if we do 0, then that gives me y equals x. We already knew that one. Or 1, that'll be y equals x plus 1 by the same algebra. Negative 5, say, for example, y equals x minus 5. And so what you'll see is that all the isoclines are on the lines with a slope of 1. So any line that has a slope of 1 is going to end up being an isocline here, okay? Because basically all we're going to do, we'll set it equal to 0, we'll set our differential equation equal to some constant, and we're going to just end up with all of our isoclines. So they're going to go up and down along basically the x-axis, right? And they'll all be these lines with slope of 1. And we'll see that when we look at the slope field. How about concavity changes? So again, we have dy dx equals y minus x. And so d squared y dx squared, for the second derivative, is going to equal dy dx minus 1. And this is then going to equal y minus x minus 1. Okay? So we set that equal to 0. Y minus x minus 1 equal to 0. And what that gives me now is that y equals x plus 1 is where all of the concavity changes. So let's take a look at this in Desmos. So looking at Desmos, what we can see is you can see some of these features, right? For example, right here, okay, right along that line of y equals x plus 1, what we get is we get that the value of the slope is going to end up equaling 1 right there, right? Okay, so you can kind of see it's just straight up right equal to 1 at that point. If we go up a little bit for y equals 2, right, now we're looking at the slope now is equal to 2, okay? And those slopes are going to be all along the line y equals x plus 2. So along this line right here, okay, you can see that the slopes there are equal to 2. Those are all of our isoclines, okay? Right? If you go over to y equals x, well, take a look at y equals x. The slopes at y equals x, those are the green ones that I'm showing you here, they're all equal to 0. We've got those 0 slopes, okay? So we've got a bunch of 0 slopes there. And then you can see that what we're going to do, and let me draw this in. So now let's draw in some solution curves. Let's say, for example, I start up here at y equals 0. Now what I know is that as I go further in the x direction, right, so as I increase the x direction, what I'm going to do is, in this case, I'm going to actually start to decrease. So if I started there, I'm going to see that this one is actually going to decrease, and it's going to decrease towards negative infinity pretty darn quickly. Okay? All right. Now, on the other hand, let's say, for example, I start up here at y equals 1. Okay? And let's say that's going to start, I'm going to increase until I hit the 0 point, and then again, I'm going to peter off. I'm going to take out the bottom. Okay? Right? What if I start out here now above that y equals 0? So now I'm going to increase, right? I'm going to increase, and that actually looks like I'm going to increase without end, right? Okay, I'm going to just like increase towards infinity, okay? Same deal, if I start down here, I'm just going to increase a little bit more slowly, and there we go, okay? What if I went in the backwards direction? Okay, again, we kind of want to think to ourselves, okay, you can kind of see that I'm going to end up having this constant slope of y equals 1, and I'm going to end up going down that line. Okay, so you can kind of see that that line at y equals x plus 1 ends up kind of being, it's not an equilibrium solution, okay, but what it does is it kind of restricts, what's going to happen with our values. It's not like we're going to, you know, if we're above it, we're going to increase without end. If we're below it, right, okay, then we're going to decrease without end, right? Okay, and that's exactly what's going to happen, okay? And so it basically ends up being, in some ways, like a slant asymptote, okay? But you kind of see that all we're going to do is we're just going to fall along those slopes until we finish, okay? Now, that completes our lecture with regards to slope fields and drawing graphs of differential equations. We're going to be doing this a lot as we work with different applications for differential equations. Remember that we've got we really have 4 features. I want you to, 1, take a look at whether or not the function depends upon only y. Does it depend upon y and x, or does it depend upon just only x? Okay, so, and that's going to tell you like basically what the basic shape of the slope field is going to look like. Secondly, we're going to look at equilibrium solutions, and those are values where the differential equation like peters out, right, and stops changing, right? It's where I get an equal 0, and it's a constant value of y where that's going to be the case. We also have isoclines, and we also have changes in concavity. All of these draw a slope field. And remember what a slope field is. A slope field is a representation of the differential equation. It's basically got all of the slopes on a particular graph. So as x and y change, what happens to the differential equation dy dx?